Thank you, Dr. Milcook, for that introduction. I would like to thank everyone for coming out to see my thesis presentation. I would like to thank the committee for coming to see my presentation on laser-assisted micromilling with minimum quantity lubrication and vortex cooling. And this will just be the general outline of our presentation. I'll start with a basic introduction of laser-assisted micromilling, the limitations of micromilling, and then we'll go into the problem statement, further go into where research is currently lacking, and then we'll go into the research objectives to show how we're going to meet those lackings. And then the rest of this presentation will go into the different approaches and the different experiments we plan to do to meet where research is left. We'll finish off with conclusions and recommendations for future. So in the past decade, technology has been miniaturizing, and because of that, manufacturing processes that can create micro and mesoscale features are greatly needed, especially in industries such as the aerospace industry, the medical industry, and the electronics industry. And here are just a few examples that show. One of the major manufacturing processes used to make meso and microscale features is micromilling. And micromilling uses micro-sized end mills. As can be seen, here's an example of a medical implant that is made with a titanium workpiece, and is being machined with a 0.2 millimeter diameter tool and a 0.4 millimeter diameter tool. Just to put that in perspective, that is a 0.2 millimeter tool is half the size of the lead in your mechanical pencils. And to give an example of that, I'll be passing out a conventional sized end mill, which you typically see in a machine shop, and a microscale end mill underneath. So, as you guys can see once you see this micro end mill, is that they're often of very small scale. They can go down to as far as 40 microns. And because of that, 40 microns in diameter, and because of that, as you can see, tools often break. Their strengths are limited because of their small size, and also because of their small size, their cutting edge radius is often on scale to the size of the grain in the workpiece, and as well as the feeds, which leads to significant plowing and rubbing of the tool, which leads to significant tool wear. And because of this, there are several approaches to help overcome these limitations. And some of those are just lowering the material removal rate. By lowering the speeds and feeds, that can greatly reduce wear. Another approach is to use tool coatings. This is another conventional technique to help reduce friction, which reduces heat to the tool. And for this presentation, we'll be focusing on some other conventional and non-conventional techniques. The first will be flood cooling. And flood cooling uses fluid to convectively remove heat from the tool workpiece interface. It also helps lubricate the tool. And as you can see here, there's just an excess amount of flow hitting this end. The next technique is minimum quantity lubrication, or MQL as we'll refer to it. And minimum quantity lubrication uses atomized oil droplets mixed with air, as seen here, and is sprayed out to the tool, very similar to as the technology as you've seen aerosol product. And because the oil droplets are so small, it is often able to better lubricate the tool workpiece interface. And in many studies, it has been shown for micromilling at least that it is as effective as flood cooling, if not more effective. The next technique is vortex cooling. And vortex cooling, as shown by this vortex air gun. It intakes compressed air and outputs very cold air without any power input, and it cools air using the Rankine-Welch effect. The next technique is a hybrid process and is not conventionally used yet, and that is laser-assisted micromilling. And the basic, to give you a basic of an idea of laser-assisted micromilling, as you can see, an end mill is run through the workpiece as shown, and simultaneously while it is removing material, a laser is pointed directly in front of the end mill as shown here, and it thermally softens the material. It is well known that by heating materials up, you can greatly increase its ductility and decrease the amount of stress needed to shear material, and this greatly reduces cutting forces. And by reducing cutting forces, it also greatly reduces wear. And this is, as has been shown in many studies, very well suited for difficult to cut alloys or hardened alloys, which we focus this thesis presentation. And just to go into some recent examples of prior work on laser-assisted micromilling, this slide shows the resultant force or the cutting forces over the duration of cutting in terms of number of grooves. And in this cutting condition, this was cut under dry cutting conditions without laser assist. And you can see the forces are fairly high, higher than the other tests, and the tool breaks after only machining 4 grooves. However, under those exact same cutting conditions with the same feeds, speeds, and depths of cut, we can see that the same situation with laser assist greatly reduced forces and thereby greatly increased the tool life. And because of this, it was able to run at 6 times the recommended yield, greatly increasing production. Another example of prior work shows how laser assist compared to dry greatly improves the tool condition. As can be seen in these cutting conditions, under the same cutting conditions, the tool chip here, and under laser assisted conditions, the tool actually looks almost new, and there's some negligible rounding, if any actually. Another example where they were machining Inconel with micro tools. Under dry cutting conditions, they're shown to have significant wear after only 6 minutes of cutting. But under the same cutting conditions with laser assist, I was able to cut twice as long with even less wear, as was shown. So a more thorough literature view of all laser-assisted micromilling studies is provided in my thesis. But where current LAM work is lacking is laser-assisted micromilling is often presented as an alternative to conventional cutting techniques, but it has only in all studies been compared to dry, which is by far the worst cutting case. It is yet to be compared to other conventional techniques such as wet or MQL or vortex cooling, which are often used in machine shops to better micro machinability, and that is lacking a systematic comparison. The next place where research is lacking is there has been no work to involve these other conventional methods to enhance laser-assisted micro machining and enhance the tool life and its micro machinability. An example is by combining MQL or vortex cooling with LAM, and that is yet to be done. So because of where research is lacking, we've come up with these research objectives. The first being we want to compare the micro machinability of a difficult to cut alloy, and for this study we decided to choose A286, which we'll explain more later on. And we would like to compare its micro machinability under dry, wet, and LAM conditions. The next objective we plan to meet is to understand the behavior of tool wear in the LAM process. over an extended duration of cutting. And we'll be doing that by running it like this. The next objective is to characterize how other methods such as MQL or Vortex could further assist laser-assisted micromilling, and we'll be observing the micromachinability again. And the approach to this is to run 3 experiments. The first objective is to conduct tests under machine tests on A286 under dry, wet, and lamb conditions. The next experiment we would like to conduct is conduct a tool life test for a prolonged period of machining under lamb. And the third test is to conduct the lamb test with MQL and Vortex. So to continue the explanation of the approach, this is just an example of our setup and system configuration, as can be seen here. So there are a lot of elements, but I'll just go into some of the main elements. As can be seen here is a zoomed in image, and as can be seen here is the spindle. The spindle is a Nakanishi spindle that's capable of reaching 6,000 RPM. Then a micro end mill is positioned in the spindle. The workpiece is mounted on top of several elements, which is driven by an X, Y, Z stage to give its tool path, to direct its tool path, and the laser the laser head points the laser directly in front of the tool path to thermally soften the material. And the laser is a Yetter beam fiber laser that is near infrared. Also for the wet assist experiments, oil is dripped onto the tool through a pipette. And just to explain the workpiece and tool we'll be using throughout all the experiments, again, as we discussed, we will be using a workpiece made out of the material A286. And A286 is a commonly used metal, especially in the aerospace industry, and it is a very attractive material to use for engineering applications because it's incredibly high tensile strength and has great corrosion resistance, and its oxidation temperature is done by the oxidation temperature. But along with these great properties, it is very difficult to machine into parts. And part of that reason is because of its very high nickel content. And because of that, it work hardens significantly more so than stainless metals. And also because of the high nickel content, it has a lower thermal conductivity, which leads to excessive heating of the tool, which greatly increases wear. Also because of its many titanium carbides that form after heat treatment, it is incredibly abrasive to the tool and the tool coating, which also accelerates tool wear. To go more into the tool, we'll be using a 0.5 millimeter diameter tool that is smaller, that's on scale with the leaded mechanical pencils, and it will be a tungsten carbide tool with a titanium aluminum nitride. And just to give an example, feel free to open this bag and use a magnifying lens to take a look at the tools. And as we stated in our research objectives, the objective was to compare the micromachinability of difficult to cut alloys such as A286 under dry, wet, and lamb cutting conditions. And to do this, we decided to run 4 assist methods: dry, wet, lamb, and lamb under 2 different parameters. The first being run at 12 watt power, and the laser parameter being run at an 18 watt parameter. And the laser was pointed at 450 microns in front of the tool with a spot size of 3. And these laser parameters were based off prior work using a thermal mechanical model produced by previous students. And these four assist methods were tested over 8 different machining conditions, which vary the cutting speed, the feed, and the depth of cut. And these parameters were chosen based off what was found in the literature review in micromachining of high nickel content outlets. And this is just an example of the experiment, as you can see. This is just showing one pass. As you can see, there's a micro tool, and this is the wet assist helping lubricate the tool with machining oil. And this is the LAM test. As you can see, a laser is pointed directly in front of the tool, as shown in the design, and it is thermally soft the material as the micromill removes material, as shown by these grooves. Very small. And you can see them better on the workpiece that is being passed around. They're very small grooves, so just make sure to use magnifying glass to see them. So this just shows the micro machinability under different cutting conditions. And for this, we just wanted to show you under dry test cutting conditions. And this shows the 8 cutting conditions showing the variations of cutting speeds, and depths of cut as shown. And I know there's a lot of pictures taken at once, but the one big takeaway is when you have a higher depth of cut, we found that the grooves had significantly more burr and significant chip adhesion along the bottom edge, as shown. And that was observed under cutting 2, 6, 4, and 8, which all had high depths of cut. And then this shows a comparison of the assist methods for a single cutting condition. And as can be seen, and as would be expected, dry cutting had the worst micromachinability with the most burr as shown. It also had a very burnished surface as seen with significant chip adhesion but still not black specks. Under wet assist, we can see that with the inclusion of cutting oil, the bottom surface is significantly smoother during the cutting process, and there is less burr, and that's probably also due to reduced shown later on. Along with these conventional techniques, here are the laser assist conditions. And as can be seen, interestingly, with LAM, with the thermal softening effect involved, we can see significantly less burr than both the conventional methods, suggesting that it is a better cutting condition. Also, the grooves are significantly less burnished than its dry condition. LAM 18 watt also had a very smooth bottom surface with minimum chip adhesion. But interestingly, because LAM 18 watt was run at a higher laser power, that led to higher temperature increase in the workpiece and more thermal softening, and made the workpiece so ductile that it created more burr than before. But noticeably, it is significantly less than the dry piece. And this is a figure just showing how the depth of cut was affected by the different assist methods. And the program target depth of cut is shown here by this dotted line, which is 20 micron deep. And as can be seen in the dry cutting condition shown green, that it tended to actually undercut the target depth of cut. That is because of tool wear as well as the elasticity of the workpiece during the cutting process. As the tool is pushing down on the workpiece tends to deflect down and leads to lower depth of cut. With the wet assist, this helped marginally reduce wear, which led to a closer to target depth of cut. But interesting, with laser assist, with the 12 watt case, you can see that the material was thermally softened and led to a more accurate depth of cut, as shown in the 12 watt case. And an interesting observation that was seen in the 18 watt case, because of the higher laser power, it led to higher temperatures, and thermal expanded the workpiece upwards into the tool during the cutting process, which led to about a plus 5 micron increase in the target in the depth of cut. Also, as discussed, we will be observing the tool and the tool wear, and as can be shown from this schematic, the flank view is shown here, and that's what these pictures show for different systems. As can be seen, the flank wear, the cutting edge is pointed out by this white arrow. It can be seen there's significant chipping here, where this edge is just completely gone. There's also significant flank wear as shown here, and also just help highlight in this white line. Under wet, there was less chipping. There is actually no chipping there, but there is still a fair amount of flank wear. And under the laser assist 12-watt condition, interestingly, it helped preserve this cutting edge. And because of that, the tool wore less and also had slightly less flank wear. Interestingly, with Lam 18-watt, which also greatly preserved the tool, one issue was because the laser was with a higher power and the workpiece was therefore at higher temperatures, it was much more ductile and more likely to stick to the position here by this logic configuration 286, and this caused significant built-up edge. That was only notable in Lam at 18. To help quantify the amount of tool wear, the tool diameter before and after was measured, before and after each experiment was measured. And these are the results for all 32 tests, but since that is also a lot to take in at once, and since all the results show the same trend, we'll just be focusing on cutting condition 3, which notably had less wear than all the other cutting conditions. And as is seen and would be expected under the dry case, there was a significantly less change in tool diameter. A significantly more amount of change in tool diameter than is seen. With wet, that helped lubricate the tool and led to slightly less tool wear, but only a marginal benefit. Interestingly, with laser assist, as shown in green, we can see that it did better than both the wet and dry case. And interestingly, with 18-watt laser power, we saw that the tool diameter increased even less. The tool diameter increased even less because of the thermal softening of the material. And along with tool diameter, we also measured the cutting forces, the average result of cutting force for all 32 experiments on both the first screw and the last screw. And because of the large amount of data, we'll just be focusing on one cutting condition since most cutting conditions have the same trend. As can be seen, the dry cutting condition had higher cutting forces for the last screw. However, with the addition of 12-watt laser, that lowered the cutting forces, and the 18-watt, due to its higher laser power and more thermal softening, but even lower forces and decreased cutting forces by almost 50%. So that is a significant benefit. So just to recap of our key findings for experiment 1. Lam 12-watt improved the groove condition with a more accurate depth cut than wet. Lam preserved the tool and reduced tool wear. In comparison to dry, on average, it reduced the change in diameter by as much as 29% compared to dry, and by as much as 21% compared to wet. So that signifies it's better than conventional wet techniques. Lam reduced the mean resultant cutting force by significantly for cutting condition 1. it decreased the result of force by 50%. So moving on to experiment 2, just to restate the objective was to understand the tool wear behavior in lamb and its effect of micromachinability and tool wear over a prolonged period of time. And unlike the previous experiment, which only machined for a very short amount, it only machined about 1.5 millimeters cubed of material. We plan to machine 150, almost 100 times more. And while doing this, we'll be conducting a tool life test under 81, under these parameters. And during this cutting process, we'll be periodically observing the micromachinability qualities by checking the group quality dimensions and also observing the tool and how it wears. So this first figure, it's a lot to take in, so I'll just go one by one. The top shows the group number that was machined and the elapsed amount of material by this group, by the time it reached this group, and also the amount of time this tool has been machined, as can be seen all the way up to the 150 millimeters cubed that we discussed earlier. Also, as can be seen, here's the top-down view of the groove and a cross-sectional view of the groove. And as can be seen in the very first case, when the tool is new, there are significant cutter marks along the bottom edge because the tool is so new. And there's also a minimal amount of or chip and heat that we can see. However, as time progresses and more material is removed and the tool wears, we can see more ununiform burrs along the edge, as is shown, and also significant burnishing. We no longer see these nice cutter marks. We see this very burnished surface along the bottom. Also, interestingly, because the tool is worn and the corner radius of the tool has increased due to tool wear, we see a bit more rounding and tapering along the edge. So there's a lot to take in, but really the only one big takeaway is the tool wears with time, and because of that burrs here, the bottom surface burnished and there's more rounding of the cross section, increasing time. And from those cross sections that we took in the previous slide, we compared the dimensional accuracy. And as you can see, when the tool is new, as shown by the blue case, it is very square, as we discussed. But after having removed 150 millimeters cubed material, we see significant rounding at the bottom of the groove, and we also see that the groove recedes inward by about 7 microns. And also we observed the tool wear as discussed. We observed the tool wear along the flank view and the bottom edge view. In the same manner, the groove numbers are given, and the amount elapsing time and volume was given. A new tool is shown for comparison, the bottom edge and the flank view. As can be seen, the flank view increases significantly with time, or increases with time, and most notably, there's a significant amount of built-up edge along the tool, and it only tends to increase with time, as shown for both views. So the one big takeaway: more machining equals more flank wear. To help quantify the amount of tool wear, several measurements were taken, including the diameter before and after, as well as the corner radius. And because all the wear measurements we took showed the same trend, we will only be showing the results for one, which is the corner radius over the elapsed amount of material removed in the tool test. And similar to what's seen in literature, we saw a very rapid increase of wear initially in the preliminary state of machining, and onwards after we see a very steady linear increase in tool wear for the remainder of the test. It is odd. So in conclusion for experiment 2, we see as the tool wore, the grooves became more rounded at the bottom, and there was significantly more burr, and the grooves also tended to taper. However, the group quality only marginally increased and only receded inward by about 7 microns, even after having machined for 25 minutes. Also shown by the tool wear results, the tool did wear very rapidly initially, but after having machined about only a third way of the way through the tool life test, it remained in steady state. And most significantly, built-up edge was very significant at the top. And here's an example of the built-up edge we saw in our experiments. And built-up edge is detrimental to the tool. Eventually, it will break off and remove some of the tool coating and could possibly even chip the tool and permanently damage it. And because of this, we wanted to ask, can MQL Vortex School prevent built-up edge? And to restate the objective that we introduced, it was to, objective 3 was to characterize how MQL and Vortex cooling affect the micromachinability of the lab process. And to do so, we ran the micromillimeters in the lab laser assist conditions under the same that was seen in experiment 1, and we ran it with 2 different MQL conditions, 2 different Vortex conditions, and these parameters were chosen off what was seen in the literature to be beneficial to tool wear. And we ran these 10 tests, but due to time, we will only be showing you the significant results from the significant tests, which are the dry and lamb, which more or less is the control in this experiment, and the lamb plus MQL2, and the lamb plus Vortex 2 is shown here. And we machined 4 groups, and we'll be showing you the results from group 1, the first group and the last group. So to kind of give an explanation of how we included MQL and Vortex into the lamb process, we would position the nozzle behind the tool as it traveled forward, and the nozzle would either cool or lubricate the tool, the backside, while the laser is directed in front, thermally softening material directly in front of the tool. And this just shows a real-life picture of the schematic is seen, the nozzles in this position here. And this was switched when the MQL was being tested. And as shown before, we'll be showing the flank and bottom edge view. And as can be seen, under the dry cast, there is significant wear. And in the lamb, there's less wear. However, there's significant amount of built-up edges. There's this large clump of APs. The most interesting result that we found from the experiment 3 was with the inclusion of MQL2, we see no built-up edge. And with Vortex, we see still some built-up edge. And to further investigate lamb plus MQL2, here is a side-by-side comparison of lamb and lamb plus MQL2 as you can see. And to help verify what we're seeing is built-up edge, EDS, electron dispersive spectroscopy was done, and the dots that you see represent the most dominant element for these, and red represents the most dominant element in the built-up edge, which is iron. Blue represents the only element in the tool substrate, which is tungsten, and green represents the most dominant element of the tool coating, which is titanium. And because of and that last slide showed where the built-up edge was forming. This shows how much built-up edge is forming. So shown in this graph is the workpiece elements shown in shades of red, and the tool elements shown in shades of blue. And as can be seen for the lamb case, we see significant built-up edge, almost 41% along that flank view of the tool. And along in the lamb plus MQL case, however, there is significantly less material workpiece adhesion or built-up edge along that edge, and that's significantly less than most. This just shows a comparison of all 3. And Vortex did marginally decrease the built-up edge compared to the lamb condition, but lamb plus MQL2 did overall reduce the built-up edge. And also we measured the tool wear as a seat, and as is shown, the dry condition, as expected, the worse in the change in tool diameter. Lamb helped benefited that, but with inclusion of MQL2 and the reduction of built-up edge, this led to less change in tool diameter, and that's just due to the lubrication effects of MQL, which greatly benefited the tool. And similarly, the same results were seen in the tool corner radius. Lamb plus MQL did significantly better. Lamb plus Vortex also did help reduce the corner radius as well. This just shows the micro machinability and the groove conditions. There's not really significant change in these grooves as to be seen, but there are some things to notice. One is that with inclusion of MQL, we saw that the burr sizes did increase. Along with that, for both Lamb plus MQL and Lamb plus Vortex 2, we see heat effect in the as seen by these streaks in the very center. And we believe that for the MQL case, with the inclusion of oil, it led to more absorptivity of the laser radiation along the top surface, which led to higher temperatures and increased heat penetration into the workpiece, more so than the depth of cut. And for the Vortex case, we see that it was also created, and we believe that's due to thermal contraction of the workpiece, which did not allow the tool to fully engage and remove all of the thermal softening material in some of the defective zones. As before, we also measured the groove depth, as shown in the dry and Lamb results correspond to what we'll see in experiment 1. But interestingly, with the inclusion of MQL, we see an increased depth of cut compared to Lamb. And again, we believe that's due to the increased laser absorptivity of the workpiece, which led to higher temperatures and more thermal expansion upwards. Interestingly, with Lamb plus Vortex, the depth of cut decreased, and that's due to the cooling effects, which thermal contracted the workpiece down, and it seemed to have almost completely compensated for the thermal expansion due to the laser. So the groove width was also measured for the first and last groove, and the difference of the groove width is shown here. And as expected, dry had the worst, Lamb benefited that, but interestingly, Lamb plus MQL had less change in groove width, suggesting that it can lead to more accurate, better dimensional accuracy. Also interesting, Lamb plus Vortex did not benefit Lamb in terms of surface roughness was also measured. The only interesting result was that dry led to a smoother surface than any of the Lamb conditions, and that's because as dry had the most tool wear. Because of tool wear, the material removal had the tool had a burnishing effect on the bottom surface of the groove, which smooths the surface because of the dull cutting edge. Also, before cutting forces were measured, no surprise that dry had highest cutting forces due to wear. Lamb helped decrease that greatly, but with inclusion of MQL, that helped decrease the cutting forces by 10%. In addition, Lamb plus Vortex 2 decreased the cutting forces by 50% compared to Lamb. So, just to give a recap of experiment 3, with Lamb plus MQL, it led to more accurate groove widths due to less tool wear, because built-up edge was prevented and the lubrication of the MQL process led to less tool wear. But one negative was that the MQL process lead to more, as we hypothesized, led to more absorption of the laser and led to an increased depth of cut. But and as the seen tool was greatly reduced in cutting forces as well were greatly reduced when including MQL to Lamb. Compared to Lamb plus Vortex did create narrower and shallower grooves and lowered the cutting forces by 50%. So the overall conclusions of experiments 1, 2, 3 are that Lamb was more beneficial than wet assist and greatly reduced tool wear, as was seen, as much on average by 21% over many different cutting conditions. Lamb greatly reduced cutting forces, and Lamb greatly increased cutting force by 50% for cutting conditions. It was also shown that Lamb enhanced tool life and allowed the tool to machine for 150 millimeters cube or for 25 minutes. And that even during this process, over this extended period of time, it only led to a marginal decrease in quality, which was shown by only a small receding by about 7 microns. Compared to Lamb, with the inclusion of MQL, this exhibited less tool wear and better groove accuracy by as much, groove width accuracy as much as 41%. MQL, and this was caused to the minimum quantity lubrication, eliminating built-up edge and reducing tool wear in the Lamb process. Vortex also marginally reduced. And from our results, some areas where research could be continued is, as we said before, we did hypothesize that MQL oil did lead to increased absorptivity, which is also suggested that oil does increase absorptivity in near-infrared lasers, as shown in the literature. Yet this needs to be further experimented or modeled by studying the laser absorptivity of minimum quantity lubrication oils under laser. And another place that could be further investigated, it has been shown that the turning process on conventional scale turning with cryogenic cooling, it has been shown that cryogenic cooling can greatly reduce tool wear. And because of this, this is yet to be investigated on the micro scale. If cryogenic cooling could be greatly focused on the tool instead of spreading all over the workpiece, as was seen in our experience, it could be beneficial to the tool as long as it does not affect the workpiece. And then studies have been done in the past, which have even by this group, studying the effects of different tool coatings in the Lamb process. However, in the last few years, many new coatings have came out with, some would say, even more beneficial properties than titanium nitride, which is used in this experiment. And no studies have yet to investigate those coatings under the Lamb process. So I would like to first greatly acknowledge my very close friend, Alberto Bucciarelli. He was my colleague during experiment 1, and he was a great assistant. None of this work would have been capable without the funding provided by Alcoa. I'd also like to thank everyone here. Many of the students at PMRC helped me during these 3 years. I'd like to also thank the faculty and the administrative staff that also made my life significantly easier. I'd also like to greatly thank the machine shop. They were a great help in fabricating much of the setup that you saw, and gave significant practical advice for experimental procedure. Many of the images you saw would have not been capable without the confocal or the scanning electron microscope that is in the IEN building. I'd also like to greatly thank my advisor, Dr. Melko, who has gave great guidance over my development here over the last 3 years. And I would also like to thank my committee, Dr. Liang and Dr. Saldana, for taking their time to be on me. I guess this is a good time to say thank you and stop and see if the audience has any questions.